Hi everyone. Today I will be just demonstrating about one new research paper from Google called as nested learning. So now in order to understand nested learning, so what we will be doing is we will be spending some time on nested learning, and then we try to understand what exactly this pre-training concepts, data pre-processing concepts, how your LLM works, so how your neural networks are learning called as back propagation. So like what is optimizers, what is activation functions, what are loss functions, what are weights. So like we will be understanding all of those concepts. So by understanding them, we will be knowing why this research paper is so important. For example, if you see, Google said what exactly this nested learning. So let's try to dive deep into this particular topic. Now here, if you are able to see, means like this is a new research paper released on November 7th 2025. So what exactly they are saying is, now very simple, if you are able to take a human, so like we, for example, as a humans, we have one concept in our brain called as neuroplasticity. What does it mean by neuroplasticity is, so whenever you are trying to use your brain, as you are using your brain, so like your brain is having an ability to learn and to unlearn, so which are not used. For example, you are not using certain parts of your brain, or you're not using certain complexity. For example, let's say you are not using learning new languages, so some part of your brain may not get used. So as you are trying to give new and new concepts or new and new challenges to your brain starts learning them, and things which are not useful to your brain or things which are not useful for a human, so it start being unlearned in a human brain. So that concept is basically called as neuroplasticity. So the ability of a brain so to expand its network, so as well as to reduce its network based on its usage, we call it as neuroplasticity. And there is another concept. For example, humans as having two types of memory. So one is called as a short term memory, and another one is called as a long term memory. So like you're able to see, so now what exactly this current LLM models, now this current LLM models, we are using ChatGPT, we are using Gemini and all of this, what these people are saying, it is more like an anterograde amnesia. So what does it mean by anterograde amnesia is, for example, take an anterograde amnesia patient, so he may not be able to remember, so he cannot remember whatever is happening right now. So like he may not be able to have a long term memory. So that is a major disadvantage with your anterograde amnesia. Now our LLM models are in the same way, so like they cannot remember anything, so like they have a static context or they have a static knowledge base. So what exactly meant by static knowledge base? For example, now if you are able to go back to this OpenAI, this one compare models, now they are trying to say we have a knowledge cutoff September 30, 2024. Even if you see another model like GPT-5 mini, they have a knowledge cutoff like May 31, 2024, or knowledge cutoff June 1, 2024. Means like whichever the models you are using right now, let's say you are using ChatGPT 5, the latest knowledge it has is of September 30. So like whichever the data they trained from the starting, whatever they scraped it from the internet from the starting till September 30th, only that context they have it. They don't have this consequent memory. For example, take a human. Now you are keep on using, so like for example, there are certain habits. Why people say if you are able to go with these habits for next 21 days or so, they're going to be more like your long term memory. Means like without your involvement, you start doing it, you feel it more easy. Now there are certain area, you, for example, now you are trying to learn about this AI, so it may be in your short term memory. As you are keep on recurrently giving that particular information to your particular brain, what happens, your brain slowly converts this short term memory into a long term memory. That's what they explained it in this particular research paper. If you are able to scroll down, so human brain comprises of two types in order to convert a short term memory into a long term memory. One, we are able to call it, if you see here, online consolidation, so like also known as synaptic consolidation phase, occurs immediately as soon after learning, even during wakefulness. This is when new and initial fragile memory traces are stabilized and being transferring from a short term to a long term storage. So this kind of facility we don't have it in LLM models. So they are static models, there is no memory to this particular LLM model. So because of that, what happens, so like whatever the knowledge it learned up to September 30, based on that it is able to give a response. So like this memory is not getting updated unless you again retrain this particular model. This memory is not getting updated. That is the limitation of your current LLM models. Means it's more like an anterograde amnesia. So like they can have a current trace but they cannot remember them. And the second one is called as offline consolidation. what exactly this offline consolidation is, when you are able to sleep, so like it is able to start generating sharp wave ripples so in the hippocampus of the brain. So like what exactly this is going to do, so they're going to slowly translate, so like again your short term memories into your long term memory. So this is what happening basically, so in your brain. Now this facility, now this people like Google is trying to work on this kind of facility in our brain. So whatever we have it in the brain, this kind of concept they are trying to do it in this artificial neural network. So like current LLM models, now they made some architectural tweak so that with the help of this nested learning, so they are trying to achieve this online base of learning. So like with the online base of consolidation, they are trying to take the short term memories and they are trying to convert into a long term memory. That's what they are trying to do. And if you are able to take, so like they are making some architectural tweak based on various brain frequencies, so like they are taking those concepts and based on that they are trying to work on certain areas. Means like if when you are taking about LLM models comprises of basically three things. One, we know data. So like apart from the data, so like what exactly influences your LLM model is the architecture, the neural network architecture. So if you are able to take our LLMs, so this is the kind of architecture we are having it. Now, apart from this architecture, the second one going to be the optimizers. So we will be learning them. So like what are optimizers? So like optimizers are responsible in making your neural networks to learn it. So in simple lines, so like optimizers, they change the optimizers, they change the neural network architecture so that they are able to create this concept of your, what is that we call it? Like they are able to create the concept of converting short-term memory into long-term memory. It's a prototype which they are trying to work on, and based on the research paper they see certain improvement. So with the help of this nested learning concept, they are able to see certain improvement in lines of the performances. Like if we scroll, yeah, here, so there are certain slight improvements. So hope is the architecture. So now here you are able to see a better performance when compared to different architectures they have it. Now in order to translate this short-term memories into long-term memories, they come up with an architecture called as hope architecture. With this they see as very smaller improvements or a smaller minor tweaks. We are able to see that. Now let's understand. Now whenever you are speaking about the models, for example, here you need to understand the intelligence power of a model is dependent on the context window and how much it is able to generate. So like what exactly context window, so how much amount of information it is able to take. For example, you have a big document, let's say 1 lakh documents, or let's say 10 lakh tokens it contains. Even though you have a 10 lakh tokens, your LLM models cannot take that as a context. So if you take ChatGPT 5, at a time they are able to take 4,000 tokens. And again, if you are able to take the maximum output, so at a time it is able to generate 1,28,000 tokens. For example, take human brain. Now in order to speak about a person, in order to make a decision, our context is very huge. So our context is very huge, and our memories are, we have a memory. So like we have a memory, we got a context, and this context is keep on updating, and it's not limited to 4 lakh tokens and all that. So like our capacities are even more bigger, so that we are able to easily able to make proper decisions at the particular goal. So like that's the reason, let's try to understand this architecture step by step. Now if you are able to take this current LLM models, so like in order to get the data, so we all know we are able to take ChatGPT, we are able to provide an input, we are able to get an output. So now what exactly we are doing now, in order to scrape the data, so there is a pre-processing. So what they will be doing, they are able to filter the data with the help of this is all data pre-processing, in order to scrape all the data from the internet. So once they are able to scrape all the data in the internet, they are able to means do all this necessary cleaning steps, so that we are able to get a cleansed data. And this cleansed data going to be especially in a one dimensional format. What does it mean by one dimensional format? So the data going to be in a pretty straight line, very big straight line. So they will be taking this kind of very huge data. It may contain 100 terabytes of data, or maybe like 200. It means as they are collecting more and more data, as they are scraping more and more data, the size of your data increases. It's a one dimensional text data. They are able to take one-dimensional text data, and this text data, like your LLM models cannot understand or your neural networks cannot understand. So now, in order to understand, so like what exactly the idea behind this, what is that LLM models or this AI is, now you are trying to take the data. When you are able to take this data with a mathematical equation, so we are able to take it in simple lines with a mathematical equation. When you are able to take the data plus a mathematical equation, the mathematical equations are able to start learning. The mathematical equations are able to start learning. What exactly meant by learning here? So like learning is also can be called as pattern extraction. So what exactly even a pattern extraction? In even layman terminology, we can say it more like a solving a mathematical equation. So in simple lines, we are able to say solving math equation. So I can say this as what? For example, it's more like you are learning. Now, in order to solve a mathematical equation, now you collected one-dimensional text data. Now this text data you cannot feed into a mathematical equation. That's completely impossible. We know that. So now your math and text, it doesn't work. So like there is a process called as encoding. So what exactly you are trying to do is, now you whatever the data you scrape through the internet with this pre-processing steps, you try to take that data and you are able to embed them into this particular numbers. For example, there is like each company has their own embedding styles or encoding style. So now for example, take what it is encoded as 4827, or it is encoded as this, you it is encoded as this, doing it is encoded as this. So like we are able to take a text data, we are able to encode it. And when you are able to pass, so what you are passing inside your neural networks, or what exactly your LLM models are learning, they are learning this encodings. LLM models are learning what? This particular encodings. Now these encodings are fed to a neural network. So what this neural network can do, it is able to start predicting the next word. So like it is able to start predicting the next word. It is able to understand this entire knowledge whichever you fed it. So it is able to understand them. So it's more like memorizing. So when you start asking questions to this particular LLM model, then it can start responding to that particular questions. So now we are taking a text data, we are translating that into numbers, we are feeding that into a neural network, and what neural network going to give as a response? It is giving a response as this number. So in simple lines, you take the text data, you are converting them, or we call it as encoding, and or we can say embedding. We are feeding that to an LLM model. So LLM model going to give a response also in encoding, and these encodings are converted into text back. So this text data we are able to call it as the prompt. So you gave a prompt so that you are able to get this text, we are able to call it as the response. So we are able to give a prompt, so you are able to get a response. So now you are giving a prompt in the natural language or in the English or whatever the language you are speaking. We are converting that into encodes, and your neural network learned your encoded information or the numbers, and that numbers again gives us again the sequence of numbers, and that numbers are converted into text back again. So like so that we are able to get a response. That's what we are able to see. Now in order to understand this particular neural network and all of this, we need to understand this particular architecture. So you are able to see this neural network. So what exactly this neural network architecture, we just need to understand. Now neural network, so now let's try to take a very simple example. Now so people who are watching this obviously have certain machine learning knowledge. Now when you are able to go back to machine learning, we have an equation in machine learning, or we in ML called as linear regression, y equal to mx plus c. So we got an equation called y equal to mx plus c. So we call in simple lines it as a simple linear regression. So we call it as a simple linear regression. Now when you are able to take the equation y equal to m1 x1 plus m2 x2 plus m3 x3 plus so on and so forth mn xn plus c, we are able to call it as a multiple linear regression. We are able to call it as multiple linear regression. Now I want to identify this unknown parameters, so m value and a c value. So if I'm able to identify unknown parameters, what happens if any new data comes in? So like what exactly the goal? For example, y equal to 3x plus 2. So like we know m value equal to 3, and c value equal to 2. Now if someone is trying to give x value, for example, this y going to be sales and this going to be pricing. So now we got an equation. So when the pricing is like, when you're able to form this equation, so based on the pricing, you're able to predict what sales. Now you know the equation 3. If the pricing is 100 rupee for a product, what gonna be the sales? So 3 into 100 plus 2. So the sales going to be 302. So like 3 into 100 plus 2, 302 going to be the sales. When your pricing is 100, your sales going to be 302. When your pricing is 1000, your price sales going to be 3 not again 3 now 3000 not something like this. So now when you are able to get a solved equation, when a new data is coming in, we are able to predict the words, or we are able to predict the whatever the next data point or whatever it is. Now in the similar lines, now we want to solve this equation. So in machine learning, what we do, in order to solve this m1 m2 m3 and all this, so we got the equations for it. For example, if I want to identify m1 m2 m3 in a multiple linear regression by using OLS concept, ordinary least square, we are able to start the equation going to be x transpose of x. So now if you have an input data, you transpose that, and this going to be input data. And once you multiplied this, you need to perform an inverse matrix -1 into x transpose into y. So like you are trying to get this, and then you are saying x transpose into y. So from this, you are able to generate intercept values and your slope values, and the intercept values you are able to generate in simple lines. Now you are trying to take your historical data, and by performing this x transpose, means in simple linear algebraic operations, you are able to get your values. But in your neural network, so now if this is the case, what happens? Now you have one set of data. For the same data, this results going to be the same. So like you have, let's say, 1 lakh data points from the internet. So for that data point, it going to give you the same result every time. It may not be having a varying result. Now if you are able to take a human brain, what happens? Now let's say you don't like a coffee, but I'm so slowly giving you coffee to drink. So like at a period, over a period of time, you start liking the coffee. You feel like, hey, this coffee is brilliant, this coffee is wonderful. You start liking it. Now how exactly what happens to a human brain is, as you are trying to feed the same data into your brain start liking it. Your brain start taking the thing so easy. For example, take this topic. You start listening to the topic, keep on. So what happens? You feel this topic so easy. Now as I'm keep on teaching this topic so frequently, I feel this topic as so easy. So that is the benefit we are able to find it with this, with the way of our learning. Now what we are doing is, now in the machine learning, we got this m's and c's are identified with the help of a fixed equation. So but in the deep learning or in the neural network, in order to invoke the ability of a human brain, what happens in a human brain? So now they can keep on learning it. It's not like one time. If the data is difficult, ML says, if a multiple linear says I cannot learn for this data, it cannot learn. You need to try with other algorithms. But humans are not like that. You can, if you are not giving up, if I'm making you to take the same data, you can achieve anything. That's how inventions have happened. Now the same concept being invoked in this neural network concept, now with the help of artificial neurons. So like now ML says I cannot learn. If ML says I cannot learn the data, it cannot learn it. Now but the deep learning is not like that. This artificial neurons are not like that. So like I can learn any kind of data. You can feed me, but I take time, I can learn any kind of data. So I can start mimicking any kind of data. So like, for example, I can generate images. If you give me a reference, I take time, but I can generate it. So that is the concept of your artificial neural network. The study of artificial neural networks, we call it as, in simple lines, we call it as deep learning. So we will be getting into that in a minute. So now what we will be doing in our regular neural network is, now let's try to take like this. So your neural network comprises of, let's say, 3 layers. So like you will be having 3 layers. They're going to be input layer. I'm writing it as node, or let's, let's say these are different nodes. Now for this particular node, I'm calling this as input node x2, x3. So there are three inputs. Now based on these three inputs, I want to predict the output. Maybe this y or this output going to be like sales. I want to predict the sales. So in order to predict it, the information need to flow from here to here. So what exactly it happens is, so in order to explain this concept, the information from this node going to travel to this particular node. Again, the information from this node going to travel to this node. Again, the information from this node going to travel to this particular node. The same way, the information from this node is traveling to this particular node. Again, the information from here is traveling to this. The information from here going to travel this. So in order to send the information from one neuron to the another neuron, so there need to be a certain weight, or we are able to call it as W. So in order to take the information from here to here, there need to be a certain importance, or we call it as weight. So I'll be explaining what is this one. Now there need to be certain importance W1, or there need to be a certain importance W2, or there need to be a certain importance W3. Again, to transfer the information from here to here, again there need to be importance W4, W5, W6. And once you got the information here, so these are called as hidden nodes. Now the information from here, it need to travel to the output node to here. So in order to send the information, again, already you got up to W6. Again, in order to transfer the information from here to here, you need to have W7, you need to have W8. So now what exactly the information we have at this particular one? So these are called as nodes, hidden nodes, H1. So now we got an input, so which is called X1. In order to transfer the information input X1 to this node, you need to have an weight called W1. So plus you got your input x2, w2 plus w3, x3 plus there going to be a bias, or we call it an unexplained variance. We call it as bias, or we can call it as error. And this is hidden node 2. So in order to transfer the information x1 to this node, so you need to have a weight w4 x1 plus w5 x2 plus w6 x3 plus b2. Now we got information h1, h2. And now what would be the output node? The information at output y going to be w7 into h1 plus w8 into h2 plus bias 3. So this would be the signal or the information we are receiving at the output. So now as you are providing this information, you are able to get this particular output. So in simple lines, you are giving the text, you need to get another text. You are giving a text, you need to get an image. So just like giving some simple examples. Now try to understand the concept like this. Now if you are able to take ML, y equal to mx plus c. In order to identify m value and a c value, you got an equation. You can just solve it. But in the neural networks, so like we cannot solve w value w2 with an equation. So how exactly we are solving them? Just take it like this. Now you know your y value, you know your x value, where y equal to 10 and where x equal to 2. So now in order to balance left hand side equal to right hand side, in order to balance left hand side is equal to right hand side, what I just need to do? So now how can I make it into both left hand side and right hand side into balance? Y equal to mx plus c. So let's say the y is 10 and the x is 2 plus, in order to balance them, I can go with different views. So I can say 3 multiplied by 2, so which is 6 plus 4. So both are equal, or 4 multiplied by 2 plus 2. This is also right. 4 multiplied by 2 plus 1. This is also right. 2 multiplied by 2 plus 6. This is also right. So in this way, there are different views for the same equation. Now the same thing. Now take the same data, take coffee, you got multiple opinions, you got multiple perspectives. So take your biryani, you got multiple perspective. Take pizza, you got multiple perspective. The same information, you got multiple perspectives. So the same thing. So now in order to identify, so as I know mathematics, so exactly I'm taking something which is multiplicable by 2 plus I'm adding it. So in order to do this, I need to know mathematics plus I need to know addition and all of this so that I can do it. But just imagine, Now you got a huge information. So like out of this huge text data, how your neural networks can identify this is the right W value. So now the goal is to identify right W values so that the difference between left hand side and right hand side is 0. So now what exactly this? The difference between left hand side and right hand side need to be 0. So that called as, so now we called as loss. So what exactly loss? The difference between left hand side minus right hand side. So now we want to identify, or we want to get the least amount of loss. If the loss is not 0, so like if the difference is not 0, so both the equation, the left hand side and right hand side, they are not equal. So you cannot say this is the exact equation. This is the not the exact W values. You cannot satisfy that. So the goal of a neural network learning is to identify the right W values. So you need to identify the right W values. If you take here, so this neural network comprises of 8 weights plus 3 biases. Overall, it contains 11 parameters. Overall, it contains 11 parameters. If you are able to take the neural networks available right now, there is like 405 billion, there is like 170 billion. So like bigger size models we are able to see. These are 11 parameters, whereas our neural networks, our LLM models are 405 billion, huge size parameters. Now, in order to balance left hand side is equal to right hand side, I need to optimize 11 parameters. So by optimizing 11 parameters, so how you can optimize it? So now we know the anchor. What is the anchor? The difference between left hand side is equal to right hand side need to be 0. So that is called as what? Loss function. So now what even OpenAI or Gemini people going to do, or any of these big companies do, they build a neural network, they pass this text data. So until the loss is 0, they keep on retaining, they keep on training it. So now until the loss is 0. So like it depends upon the kind of, so like the loss function you designed, and apart from it the architecture, the amount of data, the loss is dependent on. Now in order to optimize, I want to reduce the loss. How can I reduce it? For example, take this example, there is 3 4 5 2. I know the math, so these are the combinations. So someone can go with different combinations to balance left hand side and right hand side. Now just imagine I'm giving a big corpus of numbers, and I'm giving a for loop kind of thing or an if statement kind of thing until both are equal. It's a pointless. There are 4, not 5 billion parameters. Until them are 0, until the loss is 0, you need to try around that big corpus is a pointless. Now we want to figure out a way to solve or to identify the right W value. So like this W value need to be identified by the mathematical equation on its own. How we can do that? With the help of a concept. So how we are able to change this W values, or with the help of a concept called as optimizers. So what are they? With the help of a concept called as optimizer. So what optimizer is going to do? So we have a concept called as optimizer. So what exactly the optimizer is? Now you got your initial W value. For example, I want to have a change in W value, or we can say theta, the change in W. So I want to get a change in W theta. In order to get the change in W, I want to take the initial W value. How exactly we are taking initial W value? With the help of a random value. So what is this random value? If you are able to go back to NumPy, I can simply say np dot random dot rand n of 1. So like this command in Python, what it's going to do, it's going to generate one random value. So now this W not going to be one random value. This random value, what I do, I try to, if I'm able to take this network, so you have this particular network. Initially, I know input values x1, x2, x3. I know my y value. In the training phase, I know my y value. So now what I will be doing? I'm sorry. So like what we will be doing, so as we are having this particular random values, we try to take this W1, W2, W3, W4, W5, W6, these are all random values. So these random values are fed here into X1, X2, X3. So that X1 and H1 and H2 are generated from W1 random values, and you got H1, H2. you are trying to pass it into this equation. So again, W7, W8, B3, they are random values. H1, H2 are generated from these random values. X1, X2, X3, they are the real input parameters. In lines of LLMs, we can take X1, X2, X3 going to be my encoded values. So now these are random. When I'm able to feed it into the equation, for this input, the word need to be, maybe this encoded value need to be 2243. This is the sequence of word it need to be. Now the left hand side and right hand side may not balance. The reason why these are random values. Now what we will be doing, so now this is called as what? Forward pass. In a forward pass, you are allocating random values to weights, and in the backward process, what you are doing, you are optimizing this particular W value. So how exactly you are optimizing? Now you calculated the loss is not equal to 0. Then what I need to do in order to reduce the loss, there is only one way. I cannot change my input values, I cannot change my output value. What I can change? I can change only this random values, W1, W2, W3, B1. Now, in order to change them, so we got this optimizer equation. So W theta equal to W naught. So plus alpha into dou E by dou W. So what is dou E? Dou E is going to be loss. So dou E going to be loss. So the change in loss based on change in weight. So like what you are trying to do, you are trying to change this particular W naught minus, or it's not plus, it's minus alpha going to be the learning rate. So what exactly here learning rate is, at what speed you want to reduce your W naught value, at what speed you want to reduce your W naught value. There is another theory we will be learning about it. Again, this is called optimization. In this optimization, we got a linear optimization and a non-linear optimization. There we will be learning it better. Now, learning rate going to be at what speed you want to change your W naught values. So at what speed you want to change your W values so that the loss going to be 0. Just imagine you have a bigger learning rate, then what happens? Suddenly the value is going to have a drastical change. Maybe you are missing the exact 0 point where the loss going to be 0. You are missing that, you may cross it, you never reach that point. That's the reason what people do, they try to set this as a very smaller learning rate. So now this W naught, or the identification of a right W, may not happen at one time. So as you are training it for thousands of times, so it may be turning to be loss 0. So there is one concept, we are calling it as TensorFlow playground, I think so. Tensor board playground. There is, yeah, neural network playground. If you are able to see this, here I got a hidden layer. So if you are able to see this drawing, now here we got one hidden layer, one output layer, one hidden layer, one output layer. And in this architecture, we got one input layer, there are only 2 nodes, and one hidden layer which contain 4 nodes, and there is an output layer which contain 2 nodes. And the activation learning rate. So activation purposes, you are able to, for example, take human brain. If you are able to take human brain, all the neurons may not get activated to perform a hand movement. I want to speak. The entire brain may not get activated. Only the neural pathways which are related to hand movement are activated. So in the similar line, so I want to activate only the nodes which need to do certain tasks. So for that reason, what we are doing, we are adding an activation function. From layer to layer, there is an activation function. What activation can do is, it translate a linear signal into a non-linear signal. So like what exactly it is doing? It is able to translate a linear signal into a non-linear signal, as well as this particular activation functions are helping us in lines of firing rates. So like firing. So what exactly firing? When you are able to take given a human brain, you are getting an information. To pass the information from one neuron to another neuron, there is a firing rate. If that firing is not happening, the information may not pass from one neuron to another neuron. If you want to react to something, there need to be a firing rate. If there is no firing rate, you cannot react to something. So now activation functions are helping in lines of translating a linear signal into a non-linear signal. Now here, if you are able to see, the loss is going to be somewhere around what is that, 0.5. As if I'm able to play, as you are trying to run. So these are called iterations. What is iteration? So the very first time I change the W values. So by changing for one time, if you are able to go back now, the overall, when I just substituted random values into the equation, we got a difference of 53%. So now as I'm playing, for example, how many times? As I iterated, so 25 times I changed the W value with the help of this equation. So 25 times, I changed the value with the help of this equation. By changing for 25 times, so what happened? The loss is reduced to 0.45. Again, for another 50 times, again the loss is reduced to 0.026. So now what even the companies, big companies do, now here it's a very smaller network. So now the companies has like 405 billion. So in order to, they want to compute it for thousands of time. So until the loss is getting zero, they want to compute it. So for that reason, what they are doing, they are trying to take multiple GPUs. Why multiple GPUs? They are having a tremendous parallel processing capacity. So for that reason, so by having a tremendous parallel processing capacity, what happens? You are able to make the things more quick. So that's one of the reason what exactly these people do is like they try to take what? GPUs. Instead of CPUs, they are trying to take GPUs. So now if you take all these big companies who want to build an LLM models, the bigger models, yes, they want a GPU. That's where Nvidia is like skyrocketed like crazy. So like what happened? So like as you want a lot of GPUs, yes, Nvidia is providing those GPUs. End of the day, the high powerful GPUs are provided by Nvidia. So all of these big companies are taking them into their servers so that they can build this kind of models. Now I hope you got some understanding. Now if you take this, what we are doing now, this is called as an optimizer. This is one side of type of optimizer. There are different types of optimizers. If you see in the research paper as well, now see this. Now nested learning, okay. Over the last decades, developing more powerful neural network architectures and simultaneously designing. Okay, here I don't see good. Yes. So now if you see this research paper, now all our current learning, LLM models and all this, driven by powerful neural network architectures. Now this is one type of architecture. It's a smaller architecture. It's a simple feed-forward architecture, we call it. And now whatever LLMs we are running, so it's a very big powerful architecture. So like this is one of the architecture. Now this is nano GPT. If you take GPT-3, this is the architecture of GPT-3. So this is a huge network where exactly these are various layers you are able to have it. So what exactly this layers comprises of? This layers comprises of layer normalization, multi-head, casual self-attention, layer normalization, feed forward. So what exactly all of this? It's nothing but it's a matrix multiplication. So this comprises of matrix multiplication. It comprises of your activation functions and all of that. So like comprises of softmax activation, etc., etc. All of this we're gonna have it. And in order to means like normalize or standardize your activation, we will be using layer normalization. And in order to understand the words better, to understand the context better, we have multi-head attention and casual self-attention. So this is the kind of architecture. They are trying to take a huge amount of architecture in order to understand why you need to have this much bigger size. So as you are having the bigger sizes, your model can accommodate its learning better. It can understand the complexities better. It can understand the difficulties better. That's what even in this research paper they are trying to say. Now we got a bigger architectures. So like large, so fundamental challenge. So like what exactly the major challenge? Even though we got a bigger architecture, even though we got optimizers and all of that, still there is a problem with continual learning. So like they cannot do the continual learning. The reason why, so like whatever the questions you are asking, they cannot learn. They can just take that questions, they can respond. They're not learning that question. So for example, you keep on asking me questions, I can learn from that. The ability for a model to actually acquire new knowledge, they don't have that skill. So like whatever the model they trained till September 2024, they have that skill, but apart from it, they don't have it. They are unable to acquire new knowledge until you train them again. So now when it comes to continual learning and self-improvement, yes, I think this is all again about the human brain concept. Now, when you're able to go back to this, what this research paper says that now we got various optimizers. If you're in addition to the, again, if you're able to take, now there are different activation functions. You got optimizers and an architectural tweak. If I want to, now the data is not changing, you are getting more and more data, you are doing those pre-processing steps. So now what exactly you need to tweak? You need to change the architecture. As you tweak the architecture, you see a tremendous performance. So like in that concept, you have another one called as mixture of metrics. So like in this way, what exactly you are trying to do is, now you can change the architecture, you're able to change the optimizers. So like these are different optimizers. Atom is an optimizer, stochastic gradient descent is an optimizer, momentum is an optimizer. So these are different types of optimizers. As I change the optimizers, what is happening? There is a change in the performance, there is a change in the way the weights are getting updated. So like end of the day, again you are changing the loss as well. So how exactly you are framing the loss equation? So these are the building blocks in order to achieve what these people are doing. So now what research scientists or research engineers going to do, they keep on working on different architectural changes, architectural tweak. They are trying to work on the loss function mathematical equation. They will be working on your optimizers, change in activation function, so that they can get a better performance of your learning or whatever. Means the goal is this LLM models need to be close to the human, but right now they are not close to the human. The reason, they are static knowledge. So like whatever the knowledge we fed into these models, the same thing they have it. And what this model is going to do, they take that knowledge. Now let's go back to this architecture. Now I hope you got it. Now what is a back propagation? So now back propagation is we allocate a random weight values and we tweak or we change this random weight values with the help of optimizers until the loss is zero. So that's what we are doing. So until the loss is zero, we are keep on iterating. Now you need to keep on point in the brain. Now at a time, your LLM models or your neural networks cannot take entire data. For example, take human. Now this entire information you cannot digest at a stretch. So like you want to repeat it multiple times, you want to watch it or you want to pause it, only then you are able to understand. Now the same thing, we call it as what? Batch size. So this neural networks learn at a batch of 100, at a batch of 200, they are trying to learn. The same thing this OpenAI. So at a time it is taking a context window of 4 lakh words and learning. So now I want to increase the context window. For example, now see this is ChatGPT 4, and if I go back to ChatGPT 4.1, so ChatGPT 4.1, if I go, the context window is 10 lakh, but the maximum output token it can give is 32,000. So like the performance wise, this is not that great. That's where again GPT-5 came into the picture. So now they are trying to expand the context window. At a time they can take, even though you're giving a big prompt of 5 lakh tokens, it cannot take. So you can give a big document of 5 lakh tokens, it cannot take. The maximum window size is like 4 lakh tokens. So like that's the limitations we have it now. If so, like again the limitation is what? Whatever the corpus of knowledge it has it. So like if the knowledge is like what are the static knowledge we fed, it's not that up to the mark, again it cannot give the results up to the mark as well. Now let's go back. I hope you got an understanding how this neural networks are working. Now you got an optimizers. Now you got optimizer. So what is the purpose of optimizer? To change the weight value, to change the weight value. So now what exactly weight here? So take it in simple lines. Now you got an input, let's say 10. I cannot change the 10. So like by multiplying this W with 2 or with 0.2, as you are changing this W, it's a multiplication. As you change the W, the impact of the input can be moderated or can be reduced. So like I want to give more importance to a word, I want to give a less importance to it. How you learn it? So I want to give more importance to this, I want to learn less over a period of time. So like as you are watching something, as you are learning car driving, so like as you are keep on doing the same thing, you know when to do what. So like you allocate them, you adjust them over a period of time. You are not changing them at a stretch, you are adjusting them over a period of time. So like in order to learn your LLM models to be better, it takes time. You need to have more and more iterations, better architecture, better loss functions, and a better optimizers. So like we got an optimizer, and apart from optimizer, so we got another one which we are able to call it as loss. So the goal is what? Difference between left hand side minus right hand side. The goal is what? Until the loss is zero, the optimizer is keep on iterating. And then we have iterations. So now it cannot get a loss of zero in single go. You need to have multiple iterations. And then you got an activation function. What is the purpose of activation function? To translate linear to non-linear signal, non-linear signal. And then we got batch. So at a time it cannot take entire information. It can take a small portion of information. It can take a small portion of information. So like even though you have a huge corpus of data while you are training it, it can take only a context window of 4 lakh at a time. Based on that, it can give a response. So like you can think, as the context size increases, what happens? The intelligence power or the quality of response, it increases better. So these are the building blocks of your neural network. So now what we do, this is the architecture of neural network. Now a basic neural network architecture, any neural network is the similar concept, but the architectural tweak happens. Now what exactly we are doing, in our regular LLM models, we are trying to clean the data, we are converting them into encoding, we are feeding that into a neural network so that it can predict the next word. So it can predict the next word. Basically these models are what? They are stochastic models or probabilistic models. Means the goal is, so it read all the data. The goal is not to exactly generate the same information. So it can generate similar kind of information, varieties of information. For example, I have written, what are you doing? I'm asking different varieties of it. So like it going to take words similar to what are you doing or synonyms similar to that, and it is able to write a sentence. Now the same thing, the goal is not just to give an exact answer, but to give us a probabilistic output. So these LLM models are designed to be creative in nature, or meant to be to create more data in simple lines, or to generate different varieties of the same version. That's the basic idea of it. Now, what exactly we do? So now once you take this huge amount of data, you build a neural network architecture, the outcome going to be a base model. So what exactly we'll be getting? We'll be getting a base model. So now once you have a base model, so base model has an intelligence, but it is not trained towards conversations. It's not trained towards question answering. That's what we are doing. We are taking a raw data. So whatever the approach we are doing, right, taking this text data, converting into encoding, and passing that into this bigger architecture. So here you need a huge amount of compute power. So now it's going to have a least amount of loss. So once the least amount of loss is done, we call the training is completed. So that is called as a base model. So we take that base model, and we are able to feed a supervised approach. What exactly is meant by the supervised fine tuning? So in the supervised fine tuning, you have this kind of data. So where exactly you got various text. For this text, we can call it as a prompt. And for this text, how a human is able to give a response. So like base model has an intelligence, and then you got an instruct model. So in an instruct model, purpose is what? To perform question and answering. So now for question and answering, what these people done, they have created a question and answer example. So like they used to hire the humans, and this humans able to create various examples of questions and how to give a response. If you are able to see, this is the response for this question, this is the response provided by a human. Now they try to give these examples. We try to feed this again to a neural network. Again, we supervised fine tune. Again, we are training it. So this is not that computationally heavy. Why? You are giving how a question look like and how a response look like. So now based on this understanding, so now whenever a human is trying to ask a question, it is able to provide. So now I'm taking this base model and I'm fine tuning it, or we call this approach as post training. So I'm fine tuning it towards question and answering, so that what happens, so when we are able to use it as a chat GPT, or we are able to use it as a Gemini, that's what the process happening. Now you are able to build a neural network. So we are able to get a base model. That base model is fed to post training. In a post training, we are trying to provide this kind of question answer kind of data, so that it is able to know for this question how to give a responses. End of the day, it is not taking the same question and answering. It is using the intelligence of its previously learned data, its base model, and based on that it is giving a response. That's what happening here. Now we are able to fine tune this. So like I can fine tune it, or post training fine tuning can be done for question answering, text classification, information retrieval. Information retrieval is based on the prompt. It can search the entire internet. It can pull you the right information for you with the links. So like this is what the different varieties we are able to do it. Now if you see this entire architecture, it's a simple math plus data which is encoded, and the knowledge is static. Now the progress is a lot, like we want to work towards nested. So there is one research paper, nested learning. Now every company or this researchers are currently working towards how we can make them better, how we can take this knowledge which is static. So this base model knowledge is static. So like once I collected data from 2024, It's static. So like whatever it is trying to give a question from the static information, how can we make it dynamic? How we can make it relevant? How we can change the memory from a short term to a long term? So like I hope you got some idea and you got a pathway. So like please try to spend time on this research paper if you are interested, so which is called nested learning from Google. Try to go through that. I hope you got some good understanding of it, and you can look into this as well, the data set, how it look like. And the finally, this research paper is called as Instruct GPT. So like how exactly they take a base model, how they convert it into question answer. If you want, you can go through this particular research papers. I hope you got some understanding of it. Thank you so much. See you in the next video. If you like this kind of content, please share the comments so that I can make more content around this.